Hello, and welcome to Sleepy Engineering. In this video, we will carefully explore the history, the different types, and the working principles of one of the most influential and controversial inventions in human history, the atomic bomb. This narration is intentionally slow, steady, and repetitive. It is designed to help you relax, to focus your mind, or simply to drift into sleep. There will be no music, no sudden changes, and no emotional tone. Only the calm voice of information. Now please sit back, close your eyes if you wish, and allow the long story of the atomic bomb to unfold. The atomic bomb is one of the most powerful and historically significant inventions in the history of engineering and science. And its concept is rooted in the discovery that the nucleus of the atom contains enormous amounts of energy that can be released under specific conditions, making it possible to create explosions of unprecedented magnitude. And in order to understand the origin of the atomic bomb, it is necessary to look at the scientific developments of the late 19th and early 20th centuries, when physicists began to explore the structure of matter and discovered that atoms, once believed to be indivisible, were composed of smaller particles, such as protons, neutrons, and electrons. And from this new understanding grew the realization that splitting an atom's nucleus could release energy far greater than that produced by chemical reactions, such as combustion, leading to the idea of nuclear fission as the underlying process behind the bomb. And this concept gained further clarity in the 1930s, when scientists like Otto Hahn and Fritz Strassmann in Germany successfully demonstrated that bombarding uranium with neutrons could split the nucleus, producing lighter elements and releasing additional neutrons along with a large burst of energy, a chain reaction that could, if controlled and sustained, generate enormous power. And while this discovery opened pathways for peaceful energy production, it also suggested the possibility of designing a weapon unlike any the world had ever seen, one capable of harnessing this chain reaction to create a devastating explosion. And as political tensions rose in the years leading up to the Second World War, particularly with the rise of Nazi Germany, scientists across Europe and America became increasingly aware of the potential military implications of nuclear fission, and some of the greatest minds of the age, including Albert Einstein and Leo Szilard, warned political leaders that such a weapon might soon be developed, prompting the United States to invest in research that would ultimately result in the Manhattan Project. But at this early stage, the concept of the atomic bomb was still more theoretical than practical, and the main challenge lay in finding a way to assemble enough fissile material such as uranium-235 or plutonium-239 into a critical mass where a rapid, uncontrolled chain reaction could occur. And achieving this required not only a deep understanding of nuclear physics, but also immense advances in engineering, chemistry, and materials science. And so the first section of this story introduces us not to a finished weapon, but to the intellectual and scientific foundations upon which it was built. For the atomic bomb is not merely a product of war, but also a product of scientific curiosity, driven by decades of research into the smallest building blocks of matter. And to fully appreciate its history, it is important to keep in mind that the underlying principle, the release of nuclear energy through fission, is the same whether used for peaceful or destructive purposes. Yet when directed toward weaponry, the focus becomes the precise control of neutrons, the careful assembly of critical mass, and the design of mechanisms capable of initiating a chain reaction at exactly the right moment. And in this sense, the concept of the atomic bomb represents the crossing of a threshold in human knowledge, where the ability to manipulate the atom became the ability to reshape global politics and warfare. And thus, the introduction to this subject must emphasize both the scientific excitement of discovery and the sobering realization of its consequences. For to understand the atomic bomb, one must first understand how a simple idea, that the splitting of atoms can release immense energy, evolved into one of the defining technologies of the modern world. And in the following sections, we will trace this evolution step by step, from the laboratories of early nuclear physics to the massive wartime efforts that transformed theory into practice and ultimately produced the first atomic bombs used in conflict, shaping history forever. The early theoretical foundations of nuclear physics can be traced back to the closing years of the 19th century, when the structure of the atom was still largely a mystery, and scientists debated whether atoms were indivisible or composed of smaller components. And it was through experiments with radiation and the study of cathode rays that the first hints of subatomic structure began to appear, with J.J. Thomson's discovery of the electron in 1897, demonstrating that atoms contained negatively charged particles and thus were not the smallest possible unit of matter. And as research progressed, Ernest Rutherford's work on the scattering of alpha particles in 1911 revealed the existence of a dense nucleus at the center of the atom, leading to the nuclear model in which most of the atom's mass and positive charge resided in a compact core surrounded by electrons. And this new model fundamentally shifted scientific understanding and created the framework in which nuclear energy could later be studied. And in the 1930s, further breakthroughs came with the discovery of the neutron by James Chadwick, which provided the missing neutral component of the nucleus, enabling physicists to better explain nuclear stability and reactions, and the neutron in particular would soon prove crucial, because unlike charged particles, it could penetrate nuclei more easily, making it an ideal trigger for nuclear transformations. And around the same time, scientists such as Enrico Fermi in Italy began experimenting with bombarding various elements with neutrons, observing how nuclei captured these particles and sometimes transformed into different elements. And although Fermi initially believed he had created new transuranic elements, it was later realized that what he and others were witnessing was in fact the splitting of heavy nuclei into lighter ones, a process that would soon be recognized as nuclear fission. And this recognition came most clearly through the experiments of Otto Hahn and Fritz Strassmann in Germany in 1938, when they bombarded uranium with neutrons and found the resulting products to be much lighter elements such as barium, an observation that only made sense if the uranium nucleus had been split in two. And it was Lise Meitner, along with her nephew Otto Frisch, who interpreted this result correctly, coining the term fission to describe the process, and calculating that an immense amount of energy was released, far greater than that produced in chemical reactions. And this realization spread quickly through the scientific community, capturing the imagination of physicists who now saw that the splitting of a single nucleus released millions of times more energy than the combustion of a molecule of coal or oil. And it soon became clear that if a self-sustaining chain reaction could be engineered, where each fission released additional neutrons that caused further fissions, then a large amount of energy could be released in a very short time. And while some envisioned this as a potential new source of energy for electricity generation, others quickly grasped that it could also serve as the basis for a weapon of unparalleled destructive force, and thus the theoretical foundations of nuclear physics, built step by step through discoveries of electrons, protons, and neutrons, through models of atomic structure, and through experimental bombardments, had by the late 1930s converged into the understanding that nuclear fission was both real and immensely powerful. And it is this stage of the story that bridges the gap between pure scientific curiosity and the dawning awareness of military potential. Because once the physics was understood, the challenge became one of engineering and scale. How to gather enough fissile material, how to sustain the reaction, and how to release the energy in a controlled yet catastrophic burst. And this transition from theory to application is what would drive the next phase of the atomic bomb's history. The Manhattan Project was not only one of the largest scientific and engineering undertakings in history, but also a response to the global context of the Second World War, where the fear of Nazi Germany developing an atomic weapon pushed the United States and its allies to accelerate their efforts. And the project officially began in 1942, after warnings from scientists such as Albert Einstein and Leo Szilard convinced the American government that immediate action was necessary, and it quickly grew into a massive enterprise involving tens of thousands of people, secret facilities across the country, and unprecedented collaboration between physicists, chemists, engineers, and the military. And at its core, the project aimed to solve two enormous challenges. The first being the production of sufficient quantities of fissile material, either uranium-235 or plutonium-239, and the second being the design of a practical weapon that could harness the chain reaction of nuclear fission in an explosive device. And to achieve these goals, the United States built enormous complexes, such as Oak Ridge in Tennessee for uranium enrichment, Hanford in Washington for plutonium production, and Los Alamos in New Mexico for the design and assembly of the bomb itself under the leadership of J. Robert Oppenheimer. And each site operated under strict secrecy, with workers often unaware of the true purpose of their tasks, while at the same time immense resources were invested, with the total cost of the project reaching billions of dollars in wartime currency, making it one of the most expensive and resource-intensive projects ever undertaken. And in the global context, it is important to remember that the race to develop such a weapon was fueled by the fear that Germany, which had advanced nuclear scientists and had pioneered the discovery of fission, might be ahead. And this fear justified the urgency and secrecy of the Manhattan Project, even though it later became clear that the German nuclear program was far less advanced. And beyond the scientific and engineering challenges, the project also raised ethical and political questions among the scientists themselves, some of whom were motivated by the need to defeat fascism, while others later expressed regret that their work had contributed to weapons of mass destruction. And the cooperation between the United States, the United Kingdom, and Canada further highlighted the international nature of the endeavour, though tensions about control and secrecy foreshadowed the political struggles of the post-war period. And within the project itself, remarkable innovations took place, including new methods of isotope separation, advances in reactor design, and the development of entirely new technologies to handle radioactive materials safely. And the logistical scale was staggering, requiring the transportation of raw materials, the coordination of multiple government agencies, and the constant pressure of deadlines imposed by the war effort. And as the project neared completion in 1945, the first test of a nuclear device was carried out in the desert of New Mexico in what became known as the Trinity test, marking the first time humans unleashed the energy contained in the nucleus of the atom in a weaponized form. And this event not only confirmed the success of the Manhattan Project, but also ushered in a new era of warfare and global politics. And so when examining the history of the atomic bomb, the Manhattan Project must be seen not merely as a scientific achievement, but as a product of its global context, born of war, fear, and competition, and executed with unprecedented mobilization of resources and talent, leaving behind both technological breakthroughs and moral dilemmas that continue to resonate in discussions about science, engineering, and responsibility. The basic principles of nuclear fission form the scientific foundation upon which the atomic bomb was built. And to understand these principles, it is helpful to recall that the nucleus of an atom contains protons and neutrons bound together by powerful nuclear forces, and in very heavy elements, such as uranium and plutonium, the balance of these forces is relatively fragile, making the nuclei susceptible to splitting when they are struck by a neutron. And when a nucleus, such as uranium-235, absorbs a neutron, it becomes unstable and can divide into two smaller nuclei, known as fission fragments. And in the process, it releases a significant amount of energy in the form of kinetic energy of the fragments, gamma radiation, and crucially, additional neutrons. And it is these additional neutrons that make fission particularly powerful, because each one can go on to strike another nucleus, setting off a chain reaction. And the mathematics of the chain reaction show that if on average more than one neutron from each fission causes another fission, the reaction will grow exponentially, producing energy on a scale far beyond that of ordinary chemical reactions. And in a nuclear reactor, the challenge is to moderate and control this reaction so that it releases energy steadily for power generation. But in a bomb, the aim is to allow the reaction to grow uncontrolled, releasing all the stored energy in a fraction of a second. And the critical factor in this process is the concept of critical mass, which refers to the minimum amount of fissile material needed to sustain a chain reaction. And if the mass of uranium-235 or plutonium-239 is below this threshold, too many neutrons escape without causing further fissions, and the reaction fizzles out. But if the mass is at or above the critical level, and the material is arranged in the right shape with minimal leakage, then the chain reaction can grow rapidly, releasing enormous energy. And engineers designing a bomb face the challenge of keeping the fissile material subcritical until the precise moment of detonation, and then assembling it into a supercritical configuration almost instantaneously. And to achieve this, they devised methods such as the gun-type design, in which two subcritical pieces of uranium are rapidly slammed together, or the implosion method, in which conventional explosives compress a sphere of plutonium into a dense, supercritical state. And both rely on the same principle of fission, but differ in the way the chain reaction is initiated. And another important principle is the role of neutron initiators, which provide the first burst of neutrons to start the reaction at the exact right moment, ensuring that the chain reaction occurs when the material is most compressed and the energy release is maximized. And the physics behind fission also explain why the energy yield is so high, because according to Einstein's equation, even a small loss of mass during the splitting of nuclei is converted into a large amount of energy, and when multiplied across billions of atoms undergoing fission in less than a second, the result is an explosion with destructive power equal to thousands of tons of conventional explosives. And thus the principles of nuclear fission show both the elegance of the science and the terrifying implications of its application. Because what began as a discovery in nuclear physics became the key to a weapon that could change the course of wars and alter the balance of power between nations. And in this way, the atomic bomb stands as the most dramatic example of how a fundamental principle of physics can be transformed by engineering into an object of immense significance, both scientifically and historically. And it is for this reason that an understanding of nuclear fission is essential before examining the more detailed designs of the weapons themselves, which will be explored in the next sections. The design and functionality of uranium-based atomic bombs center on the use of uranium-235, a rare isotope of uranium that is capable of sustaining a rapid chain reaction. And because natural uranium contains mostly uranium-238 with less than 1% uranium-235, the first challenge faced by engineers was the enrichment process, a difficult and resource-intensive task that required separating the lighter uranium-235 atoms from the heavier uranium-238 atoms, using techniques such as gaseous diffusion, electromagnetic separation, and later centrifuges. And once sufficient enriched uranium was obtained, the problem shifted to how to arrange it so that it would remain safe and subcritical during handling and transport, yet could be brought together into a supercritical mass at the moment of detonation. And the gun-type design emerged as the most straightforward solution for uranium-based weapons, and this design worked by taking two subcritical pieces of uranium-235, often shaped as cylindrical slugs or blocks, and rapidly driving one into the other using a conventional explosive charge, so that when they combined, they formed a single supercritical mass in which a chain reaction could develop. And in this configuration, the timing was crucial, because if the pieces came together too slowly, some neutrons might start the chain reaction before full assembly, leading to a premature detonation known as a fizzle. And to prevent this, engineers relied on carefully designed mechanisms that ensured rapid acceleration and alignment. And when the two uranium components finally merged, the neutron population rose exponentially, and the energy was released in an immense explosion. And in order to guarantee that the chain reaction would ignite at the optimal moment, many designs also included a neutron initiator, a small device that emitted a burst of neutrons precisely when the mass became supercritical, thus ensuring reliable performance. And the most famous uranium bomb was the device dropped on Hiroshima in August 1945, known as Little Boy, which used a gun-type assembly with about 60 kilograms of uranium-235, and the detonation produced an explosion equivalent to roughly 15 kilotons of TNT, devastating the city and demonstrating the terrible power of uranium fission. And this bomb had not been tested before use, because scientists were confident in the simplicity of the design, though its efficiency was relatively low, with only a small fraction of the uranium actually undergoing fission before the device blew itself apart. Yet the yield was still far greater than any conventional weapon. And this underlines an important aspect of uranium bombs, which is that while they are technically simpler to design than plutonium devices, the difficulty lies in producing the enriched uranium in sufficient quantities, making the enrichment process the true bottleneck in uranium bomb production. And the physics behind the detonation are straightforward. As the rapidly assembled uranium-235 reaches a supercritical state, neutrons multiply in a chain reaction, and within less than a microsecond, the release of energy causes temperatures of millions of degrees and pressures strong enough to vaporize the bomb casing and create a massive blast wave. And so uranium-based bombs embody both simplicity and difficulty, being simple in concept and assembly, but enormously challenging in terms of material preparation. And historically, their use demonstrated the feasibility of fission weapons in the most direct way, providing a model that remains part of the discussion of nuclear weapons development even decades later. And the legacy of the uranium bomb is inseparable from its place in history as the first atomic weapon ever used in warfare, a weapon that revealed not only the destructive potential of nuclear energy, but also the engineering challenges that had been overcome to harness it. And thus, the uranium-based bomb stands as a key chapter in the broader story of atomic weapons, bridging the gap between theoretical possibility and devastating reality. The plutonium-based bomb design differs from uranium bombs, both in the type of fissile material used and in the engineering methods required to make it work. And while uranium-235 could be utilized in a relatively simple gun-type design, the characteristics of plutonium-239 made such an approach impractical, and plutonium-239 is not found in nature in usable quantities, but is instead created artificially in nuclear reactors, when uranium-238 captures neutrons and undergoes a series of transformations. And once separated chemically from the reactor fuel, this isotope becomes highly fissile and capable of sustaining a chain reaction. But it also presents complications, because reactor-produced plutonium contains impurities, such as plutonium-240, which has a high rate of spontaneous neutron emission. And this means that if one tried to assemble a plutonium bomb by simply slamming two pieces together, as in the uranium design, the reaction would begin too early and cause a fizzle instead of a full explosion. And to solve this challenge, engineers developed the implosion method, which became the hallmark of plutonium bombs. And in this design, a sphere of plutonium is surrounded by carefully arranged conventional explosives that, when detonated simultaneously, compress the plutonium core to a much higher density. And this rapid compression brings the material to a supercritical state before the spontaneous neutrons can spoil the reaction. And to achieve perfect symmetry in the implosion, engineers had to invent explosive lenses, shaped charges that controlled the blast waves from multiple detonators and focused them inward evenly, creating the uniform shock necessary to compress the plutonium core. And at the center of the core, a neutron initiator was placed to inject a burst of neutrons at the exact moment of maximum compression, ensuring the chain reaction began at the right time. And the implosion method represented a much more complex engineering achievement than the gun-type design, requiring precise timing, advanced explosives engineering, and extensive testing. But it was the only practical way to utilize plutonium as a bomb material. And the most famous example of this design was the device known as Fat Man, which was dropped on Nagasaki in August 1945, producing a yield of about 21 kilotons of TNT. And unlike Little Boy, the plutonium bomb had been tested in advance during the Trinity test in July 1945 in the New Mexico desert, which confirmed that the implosion method worked and marked the first detonation of a nuclear device in history. And the success of the plutonium design had major implications for nuclear weapons development, because plutonium could be bred in large quantities in reactors and did not require the massive industrial enrichment facilities needed for uranium-235. And this made it a more practical path for building larger arsenals, though at the cost of far more sophisticated bomb designs. And from a physical perspective, the explosion of a plutonium bomb follows the same principles as any fission device, with the chain reaction releasing immense energy in less than a microsecond, creating temperatures hotter than the sun's core, pressures strong enough to compress matter beyond ordinary limits, and blast waves that can devastate entire cities. And the use of implosion also opened the door to future innovations, such as boosted fission and thermonuclear weapons, because once engineers learned how to compress fissile material with explosives, they could apply the same principles to more advanced designs. And thus the plutonium bomb represents not only a major milestone in the wartime history of nuclear weapons, but also a foundation for the further evolution of nuclear technology, embodying both the complexity of advanced engineering and the devastating consequences of its success. And it remains one of the most significant achievements of the Manhattan Project, and a symbol of the rapid progression from theoretical discovery to destructive application. The plutonium-based bomb design differs from uranium bombs, both in the type of fissile material used and in the engineering methods required to make it work. And while uranium-235 could be utilized in a relatively simple gun-type design, the characteristics of plutonium-239 made such an approach impractical, and plutonium-239 is not found in nature in usable quantities, but is instead created artificially in nuclear reactors, when uranium-238 captures neutrons and undergoes a series of transformations. And once separated chemically from the reactor fuel, this isotope becomes highly fissile and capable of sustaining a chain reaction. But it also presents complications, because reactor-produced plutonium contains impurities, such as plutonium-240, which has a high rate of spontaneous neutron emission. And this means that if one tried to assemble a plutonium bomb by simply slamming two pieces together, as in the uranium design, the reaction would begin too early and cause a fizzle instead of a full explosion. And to solve this challenge, engineers developed the implosion method, which became the hallmark of plutonium bombs. And in this design, a sphere of plutonium is surrounded by carefully arranged conventional explosives that, when detonated simultaneously, compress the plutonium core to a much higher density. And this rapid compression brings the material to a supercritical state before the spontaneous neutrons can spoil the reaction. And to achieve perfect symmetry in the implosion, engineers had to invent explosive lenses, shaped charges that controlled the blast waves from multiple detonators and focused them inward evenly, creating the uniform shock necessary to compress the plutonium core. And at the center of the core, a neutron initiator was placed to inject a burst of neutrons at the exact moment of maximum compression, ensuring the chain reaction began at the right time. And the implosion method represented a much more complex engineering achievement than the gun-type design, requiring precise timing, advanced explosives engineering, and extensive testing. But it was the only practical way to utilize plutonium as a bomb material. And the most famous example of this design was the device known as Fat Man, which was dropped on Nagasaki in August 1945, producing a yield of about 21 kilotons of TNT. And unlike Little Boy, the plutonium bomb had been tested in advance during the Trinity test in July 1945 in the New Mexico desert, which confirmed that the implosion method worked and marked the first detonation of a nuclear device in history. And the success of the plutonium design had major implications for nuclear weapons development, because plutonium could be bred in large quantities in reactors and did not require the massive industrial enrichment facilities needed for uranium-235. And this made it a more practical path for building larger arsenals, though at the cost of far more sophisticated bomb designs. And from a physical perspective, the explosion of a plutonium bomb follows the same principles as any fission device, with the chain reaction releasing immense energy in less than a microsecond, creating temperatures hotter than the sun's core, pressures strong enough to compress matter beyond ordinary limits, and blast waves that can devastate entire cities. And the use of implosion also opened the door to future innovations, such as boosted fission and thermonuclear weapons, because once engineers learned how to compress fissile material with explosives, they could apply the same principles to more advanced designs. And thus the plutonium bomb represents not only a major milestone in the wartime history of nuclear weapons, but also a foundation for the further evolution of nuclear technology, embodying both the complexity of advanced engineering and the devastating consequences of its success. And it remains one of the most significant achievements of the Manhattan Project, and a symbol of the rapid progression from theoretical discovery to destructive application. The Fat Man bomb was the second atomic weapon used in warfare, and it represented the far more complex implosion design that had been developed to make use of plutonium-239. And unlike the gun-type uranium bomb known as Little Boy, Fat Man relied on a carefully engineered mechanism to compress a plutonium core into a supercritical state before spontaneous neutrons could cause a premature reaction. And the bomb itself was roughly 3.5 meters long, over 1.5 meters in diameter, and weighed about 4.5 tons, giving it a bulky shape that inspired its nickname. And at the heart of the device was a plutonium core surrounded by a tamper of natural uranium that helped reflect neutrons inward and improve efficiency. And around this tamper were layers of high explosives arranged in a spherical pattern, and the explosives were divided into segments fitted with shaped charges that acted as lenses, directing the force of the detonation inward in a perfectly symmetrical implosion. And when the bomb was triggered, dozens of detonators fired simultaneously, sending shock waves into the plutonium core and compressing it to a density several times greater than normal. And in that instant, the core went from subcritical to supercritical, allowing the chain reaction to begin. And at the very center of the core was a small neutron initiator, often referred to as the polonium-beryllium device, which emitted a burst of neutrons exactly at the moment of maximum compression, ensuring that the chain reaction started under ideal conditions. And this design required extraordinary precision, because any asymmetry in the implosion would prevent the plutonium from reaching the necessary density. And developing this precision had been one of the most difficult engineering challenges of the Manhattan Project, requiring extensive testing and innovation. And the success of the Trinity test in July 1945 proved that the implosion design could work, giving confidence that Fat Man would function as intended. And the bomb was dropped by the B-29 bomber Bockscar on August 9, 1945, over the city of Nagasaki, and it exploded with a yield of about 21 kilotons of TNT, even greater than Little Boy, causing massive destruction and loss of life. And from a technical standpoint, Fat Man was far more efficient than its uranium counterpart, using less fissile material, but achieving higher yield, thanks to the implosion method. And its design also demonstrated the future direction of nuclear weapons technology, because plutonium could be produced in reactors on a large scale, making implosion devices more practical for building arsenals. And the structure of Fat Man thus combined the plutonium core, the uranium tamper, the neutron initiator, and the explosive lenses into a unified mechanism that harnessed the principles of fission in the most effective way known at the time. And while its immediate effect was the devastation of Nagasaki, its long-term significance was to show that nuclear engineering had reached a level of sophistication that made mass production of bombs possible. And studying its mechanism reveals the intersection of physics, chemistry, metallurgy, and explosives engineering, all brought together in a weapon whose destructive power altered the course of the 20th century. And the Fat Man bomb remains a defining example of how scientific discovery, when combined with industrial capability, can produce technology of immense impact, embodying both the brilliance of human ingenuity and the tragic consequences of its application. And in understanding its structure and mechanism, we gain deeper insight into the path that led from the first theoretical discoveries of nuclear physics to the reality of modern nuclear arsenals. The immediate effects of the first uses of atomic bombs in warfare were unlike anything the world had ever seen, and when Little Boy detonated over Hiroshima on August 6, 1945, and Fat Man followed over Nagasaki on August 9, 1945, the cities were instantly transformed by forces that defied previous human experience. And at the moment of detonation, temperatures at the core of the explosions reached several million degrees Celsius, creating a fireball that expanded at tremendous speed and generated intense light that was visible for miles. And within fractions of a second, the thermal radiation ignited fires across vast areas, burning wood, paper, cloth, and even scorching human skin at great distances. And those close to the hypercenter were vaporized instantly or left with fatal burns. And the blast wave followed the fireball with devastating force, flattening buildings, bridges, and infrastructure over large parts of the cities. And the pressure created was several times greater than that of the strongest conventional bombs, demolishing wooden houses completely and toppling reinforced structures. And the combination of blast and fire created a firestorm in Hiroshima that consumed much of the city, while in Nagasaki, the hilly terrain confined the damage but still destroyed large districts. And in addition to the thermal and blast effects, the bombs released intense ionizing radiation that penetrated the bodies of survivors, damaging cells and organs and causing acute radiation sickness, symptoms of which included nausea, vomiting, hair loss, internal bleeding, and eventual death for many. And those who survived the initial explosion often suffered from burns, injuries from collapsing buildings, and radiation exposure simultaneously, overwhelming the limited medical facilities that remained intact. And the immediate casualties in Hiroshima are estimated to have been between 70 and 80,000 people, with tens of thousands more dying in the following weeks, while Nagasaki saw around 40,000 killed instantly, with many thousands more succumbing later. And beyond the human toll, the bombs also destroyed the physical environment, turning urban landscapes into charred ruins, contaminating water supplies, and leaving behind zones of rubble that bore little resemblance to the thriving cities that had existed before. And the psychological shock was equally profound, as survivors known as hibakusha struggled to comprehend what had happened. And as news of the devastation spread, governments and militaries around the world realized that warfare had entered a new era, and the Japanese government, already weakened by years of conflict and conventional bombing, faced the reality that further atomic attacks could follow. And within days, Japan announced its surrender, ending the Second World War. And so the immediate effects of the first uses of atomic bombs were not only the physical destruction and human suffering in Hiroshima and Nagasaki, but also the rapid transformation of global politics, as the weapon demonstrated its power so clearly that it reshaped the course of history. And from an engineering perspective, these events showed that the designs of Little Boy and Fat Man had worked as intended, unleashing the energy of nuclear fission on a scale large enough to obliterate cities. And the combination of thermal radiation, blast pressure, and radiation exposure defined the unique character of nuclear weapons, marking them as unlike any conventional explosives used before. And while later discussions often focus on the long-term consequences, the immediate aftermath of the first uses stands as a stark reminder of the destructive capacity that arises when theoretical physics and large-scale engineering converge in the form of weapons. And it is within these events that the world first understood the reality of the atomic bomb, not as a scientific idea or a test in the desert, but as a devastating force unleashed on human populations, forever changing the perception of war, science, and human responsibility. The development of thermonuclear weapons marked the next stage in the evolution of nuclear arms, as scientists and engineers sought to harness not only the energy of fission, but also the far greater power of nuclear fusion. And whereas fission bombs relied on the splitting of heavy nuclei such as uranium-235 or plutonium-239, fusion bombs exploited the merging of light nuclei such as deuterium and tritium into heavier elements, a process that occurs naturally in the sun and that releases vastly more energy per reaction. And the idea of combining fission and fusion was considered as early as the Manhattan Project. But the technical challenges were enormous, because achieving the extreme temperatures and pressures necessary to ignite fusion on Earth required innovative designs that went beyond the relatively straightforward mechanisms of fission devices. And after the war, the Cold War rivalry between the United States and the Soviet Union created a political and military climate in which both sides felt compelled to pursue thermonuclear weapons, often referred to as hydrogen bombs. And the key breakthrough came in the early 1950s with the Teller-Ulam design, named after physicists Edward Teller and Stanislaw Ulam, which solved the problem of how to compress and ignite the fusion fuel. And this design used a two-stage process in which a primary fission bomb provided the initial energy and a secondary stage containing fusion fuel was compressed and heated by the radiation and shock waves from the primary, creating conditions where deuterium and tritium nuclei could fuse and release tremendous energy. And to make the process more efficient, materials such as lithium deuteride were employed because they could generate tritium during the explosion, serving as additional fuel. And the result was a device whose explosive yield could be hundreds or even thousands of times greater than the bombs used at Hiroshima and Nagasaki. And the first full-scale test of such a weapon was conducted by the United States in 1952 in the Pacific Ocean, and produced a blast of several megatons, obliterating an entire island and demonstrating a destructive capacity that dwarfed all previous weapons. And the Soviet Union followed with its own successful thermonuclear test in 1953, initiating a new phase of the arms race in which both nations rapidly developed increasingly powerful hydrogen bombs. And the engineering of these devices required not only mastery of nuclear physics, but also advances in explosives, materials science, and precision timing, since the synchronization of stages and the control of radiation implosion were essential to achieving fusion ignition. And thermonuclear weapons also introduced the concept of scalability, because by adjusting the amount of fusion fuel and the configuration of the stages, yields could be tailored from smaller tactical devices to enormous strategic weapons. And this flexibility made them central to military planning during the Cold War. And the existence of such weapons transformed global politics, because the destructive potential of a single bomb was enough to threaten entire nations, giving rise to doctrines of deterrence and mutual assured destruction. And from a scientific standpoint, the development of thermonuclear weapons showed the ability of humans to replicate on Earth the processes that power stars, turning astrophysical phenomena into tools of war. And the consequences of this achievement were profound, because it meant that humanity now possessed the ability not merely to destroy cities, but to devastate entire regions and potentially alter the balance of life on the planet. And thus, the development of thermonuclear weapons, represents both the peak of nuclear engineering and the height of human capacity for destruction, standing as a testament to the relentless pursuit of technological power and the new dangers it brought to the world. The hydrogen bomb, also known as the thermonuclear bomb, operates on the principle of nuclear fusion, the same process that powers the sun, and its design represents one of the most complex achievements in the history of engineering, because it not only builds on the foundations of fission, but also extends them to unleash energy on a scale far beyond that of earlier atomic bombs. And the principle at its core is that when light nuclei, such as deuterium and tritium, combine to form heavier nuclei, such as helium, the difference in mass is converted into energy according to Einstein's equation E equals mc2, and the energy released per fusion reaction is far greater than that of fission. But the challenge lies in creating the extreme temperatures and pressures necessary for fusion to occur, conditions that are only naturally found in stars. And to achieve this on Earth, the hydrogen bomb uses a staged design in which a fission bomb serves as the primary trigger. And when detonated, this primary explosion produces immense heat and a flood of X-rays that compress and ignite a secondary stage containing the fusion fuel. And the design that solved this engineering challenge is known as the Teller-Ulam configuration, in which radiation from the fission primary is channeled into a separate chamber holding the secondary, and this radiation implosion compresses the secondary fuel to densities and temperatures sufficient for fusion, and in addition to deuterium and tritium, the secondary often contains lithium deuteride, a solid compound that under the intense conditions of detonation generates tritium, ensuring a continuous supply of fusion fuel. And to enhance efficiency, the secondary is often surrounded by a tamper, typically made of uranium, that reflects neutrons inward and helps sustain the reaction. And because the fusion reaction produces fast neutrons with much higher energy than those from fission, these can in turn cause further fission in the tamper, greatly increasing the overall yield, and thus the hydrogen bomb is actually a combination of fission and fusion working in sequence, with the fission primary igniting the fusion secondary and the fusion neutrons driving additional fission, creating a cascading release of energy that can reach millions of tons of TNT equivalent. And the first test of such a device by the United States in 1952 demonstrated this principle, producing a multi-megaton explosion that vaporized an island and carved a massive crater in the ocean floor. And subsequent designs became more compact, efficient, and adaptable, making them suitable for deployment on missiles, aircraft, and submarines. And the engineering of hydrogen bombs required precise control of timing, symmetry, and material selection, because the slightest flaw in compression or ignition could prevent fusion from occurring. And yet, when successful, the design yielded an explosion many times more powerful than fission bombs, with effects including enormous fireballs, blast waves capable of leveling cities over wide areas, intense thermal radiation igniting fires hundreds of kilometers away, and radiation fallout spreading across continents. And the hydrogen bomb thus represents both the pinnacle of nuclear weapons technology and a symbol of the dangers of unchecked scientific advancement, because its design illustrates how a fundamental natural process can be replicated and magnified by human ingenuity into a weapon of unimaginable power. And in studying the hydrogen bomb's fusion principles and design, one sees the culmination of decades of research in physics and engineering applied to the most destructive purpose possible. And the existence of such weapons reshaped international relations, military strategies, and the very nature of global security. For once, the hydrogen bomb was built. The scale of human warfare was forever altered, and the line between scientific exploration and existential threat became inseparably blurred. The effectiveness of atomic and later thermonuclear weapons has always depended not only on the design of the bombs themselves, but also on the systems used to deliver them to their targets. And the engineering challenges associated with these delivery systems have shaped much of the history of nuclear weapons development, because a weapon of immense power is only useful if it can be transported safely, accurately, and reliably to its intended destination. And in the earliest stage of nuclear warfare, the delivery method was the strategic bomber, as demonstrated by the B-29 aircraft that carried Little Boy to Hiroshima and Fat Man to Nagasaki. And designing bombs for delivery by aircraft required attention to size, weight, and aerodynamics, because the bombs were massive devices that had to be carried long distances and released at precise altitudes. And engineers also had to design arming mechanisms that would prevent accidental detonation during flight and ensure proper detonation above the target. And as nuclear weapons advanced in power and sophistication, new delivery methods were sought, leading to the development of ballistic missiles, which represented a major engineering leap, because a missile had to carry a heavy warhead across continents, withstand re-entry into the Earth's atmosphere, and strike with great accuracy, and this required innovations in rocketry, guidance systems, and heat shielding. And the Soviet launch of intercontinental ballistic missiles in the 1950s demonstrated that nuclear weapons could be delivered without aircraft, altering the balance of global power. And the United States and the Soviet Union both invested heavily in missile programs, creating arsenals of land-based ICBMs, as well as submarine-launched ballistic missiles that gave nuclear forces greater survivability and second strike capability. And each of these systems presented unique engineering challenges, such as miniaturizing warheads to fit onto missile tips, ensuring structural integrity under extreme acceleration, and developing reliable guidance technologies that could correct for errors over thousands of kilometers. And another major aspect of delivery system engineering was safety, because nuclear warheads had to be secured against accidental detonation during transport, storage, or malfunction, leading to the development of fail-safe mechanisms, permissive action links, and elaborate arming sequences that could only be activated by authorized personnel, and the concept of multiple independently targetable re-entry vehicles, or MIRVs, emerged in the 1960s and 1970s, allowing a single missile to carry several warheads that could strike different targets, greatly increasing destructive potential and complicating defense systems. And beyond missiles and bombers, other platforms such as artillery shells, depth charges, and even experimental nuclear landmines were developed, each requiring specialized engineering to adapt the nuclear principle to a specific military role. And yet the most enduring challenge has always been the balance between destructive power and practical usability, because weapons too large or difficult to deliver would not serve military strategies. And so much of the history of nuclear weapons is a history of making them smaller, lighter, and more efficient while maintaining or increasing their yields. And this constant drive for optimization pushed advances not only in nuclear physics, but also in aerospace engineering, electronics, and materials science. And ultimately, the story of delivery systems shows how the atomic bomb was never just a scientific breakthrough, but also an engineering problem of immense complexity, requiring solutions that integrated aircraft design, missile technology, guidance systems, and safety controls. And the success of these efforts is evident in the fact that modern nuclear weapons are compact, reliable, and deployable from multiple platforms, a reality that ensures their continuing role in global security and strategy. And it is through these engineering challenges and solutions that the raw power of nuclear reactions has been transformed into practical instruments of war, making delivery systems an inseparable part of the history and function of the atomic bomb. The testing programs for nuclear weapons were essential to transforming theoretical designs into reliable devices. And from the very beginning, scientists and military leaders understood that only through actual detonations could they confirm the effectiveness, yield, and functionality of such unprecedented technologies. And the first of these was the Trinity test in July 1945 in the New Mexico desert, where the implosion design using plutonium was proven to work. And that detonation not only validated the engineering of explosive lenses and neutron initiators, but also revealed the immense destructive capacity of a real atomic device. And in the years after the war, nuclear testing expanded rapidly as nations sought to refine designs, measure effects, and demonstrate capability. And each test served technical objectives, such as determining the efficiency of different bomb geometries, the performance of new materials, and the scaling of yields from kilotons to megatons. And atmospheric tests in the Pacific and Nevada deserts provided visual confirmation of blast waves, fireballs, and mushroom clouds, which were studied using high-speed photography, pressure sensors, and airborne instruments, and engineers carefully analyzed data on shock propagation, thermal radiation, and fallout distribution to improve weapon reliability and predict effects on targets. And another major technical objective was miniaturization, because early bombs were enormous and difficult to deliver. So tests helped in creating lighter warheads suitable for missiles and aircraft. And as thermonuclear designs emerged in the 1950s, testing became even more critical, since the Teller-Ulam concept involved complex interactions between a fission primary and a fusion secondary, and experiments such as the 1952 Ivy Mike test by the United States demonstrated multi-megaton yields and confirmed the practicality of fusion-based weapons, while the Soviet Union conducted its own series culminating in the 1961 Tsar Bomba test with a yield of 50 megatons, the largest ever detonated. And beyond raw power tests, also focused on safety and control, exploring how weapons behaved under different conditions, including partial failures or altered geometries, because understanding the margins of error was essential to ensuring predictable outcomes. And underground testing programs began in the late 1950s as concerns about radioactive fallout grew, and these allowed engineers to continue experiments while reducing atmospheric contamination. Though they presented new challenges in containment and measurement, requiring the drilling of deep shafts and the installation of sensors to record seismic activity and gas release. And one key technical goal of testing was to improve accuracy in predicting yield, because early estimates often diverged widely from actual results, and through repeated experiments, models were refined to better match reality. And testing also played a role in developing defensive knowledge, as governments measured the effects of nuclear blasts on buildings, vehicles, ships, and even live animals to understand potential vulnerabilities and plan for civil defense. And throughout these decades, the sheer number of tests, over 2,000 worldwide by the early 21st century, reflected both the technical demands of weapon development and the political symbolism of demonstrating nuclear strength, and eventually treaties such as the Partial Test Ban Treaty of 1963 and the Comprehensive Nuclear Test Ban Treaty of 1996 sought to limit or end such tests. But even with restrictions, nations developed computer simulations and subcritical experiments to pursue the same technical objectives without full-scale detonations. And so the history of nuclear testing programs shows how science, engineering, and politics converged in the pursuit of data, reliability, and deterrence. And it underscores the reality that each advance in nuclear weapon design was built not only on theory, but on the measured results of controlled yet devastating explosions, which provided the knowledge necessary to turn concepts into operational arsenals. During the Cold War, the development of nuclear weapons entered a phase where the focus was no longer only on increasing explosive power, but also on miniaturization. And the engineering challenges of making nuclear warheads smaller, lighter, and more versatile became central to military strategy, because the ability to mount warheads on a variety of delivery systems from long-range missiles to submarines and even artillery required compact designs. And the earliest atomic bombs of the 1940s were large and heavy devices that could only be carried by specially modified bombers. But as missile technology advanced, there was an urgent need to reduce both size and weight without sacrificing yield. And this process demanded breakthroughs in metallurgy, explosives engineering, and precision machining. And scientists learned how to shape implosion systems more efficiently, using fewer explosives while still achieving the necessary compression of the core, and improvements in neutron initiators and tamper materials also allowed for smaller quantities of fissile material to achieve the same or greater yield. And in the 1950s and 1960s, the United States and the Soviet Union both achieved significant progress, creating warheads compact enough to fit atop intercontinental ballistic missiles, a shift that redefined the nuclear balance of power because it meant nuclear strikes could be delivered across continents in minutes, and further advances came with multiple independently targetable re-entry vehicles, or MIRVs, where a single missile could carry several smaller warheads, each capable of striking different targets. And this required miniaturization at an even greater scale since several compact warheads had to fit into one missile payload. And another important development was the creation of tactical nuclear weapons designed for use on the battlefield rather than for strategic city-destroying missions. And these included nuclear artillery shells, depth charges for anti-submarine warfare, and even portable demolition charges, all of which relied on miniaturization to make nuclear devices adaptable to specific military roles. And the engineering required to achieve this level of flexibility pushed research into advanced high-explosive lens systems, boosted fission techniques where small amounts of fusion fuel improved efficiency, and new alloys and materials that could withstand the stresses of deployment, and miniaturization also improved safety, because smaller devices could incorporate more reliable arming mechanisms and better control systems, reducing the risk of accidental detonation, and that to produce lightweight warheads also expanded delivery options to include submarines and mobile launchers, making nuclear forces harder to detect and destroy. And this survivability strengthened doctrines of deterrence by ensuring that no side could launch a first strike without facing devastating retaliation. And throughout the Cold War, the quest for miniaturization was not only a technical challenge, but also a political necessity, because each superpower measured its credibility and deterrence by the diversity and readiness of its nuclear arsenal, and the successful miniaturization of warheads meant that nuclear weapons could be deployed globally on a scale and with a flexibility that had never before been possible. And from an engineering perspective, these achievements required constant refinement of manufacturing precision, explosive design, and nuclear physics, as every reduction in size demanded greater accuracy in timing and symmetry, and the outcome was a generation of nuclear weapons that were no longer gigantic prototypes, but standardized, reliable, and versatile tools of military strategy. And thus the Cold War advances in bomb miniaturization represent one of the most important phases in the history of nuclear weapons, showing how the pursuit of engineering efficiency transformed them from cumbersome devices into integrated components of global arsenals, changing the dynamics of deterrence, warfare, and international relations in profound ways. The story of nuclear weapons is not only about their invention and refinement, but also about the international treaties and technical limitations that sought to control their spread and use. Because from the moment the first bombs were dropped in 1945, it became clear that such weapons posed a threat to humanity itself. And as the Cold War intensified, the superpowers recognized that an uncontrolled arms race could spiral into catastrophe. And one of the earliest efforts was the 1963 Partial Test Ban Treaty, which prohibited nuclear tests in the atmosphere, in outer space, and underwater, driven by growing concerns about radioactive fallout and its harmful effects on populations and the environment. And this treaty forced weapons laboratories to turn increasingly to underground testing, which required different engineering methods to measure yields and contain radiation. And later agreements, such as the 1968 Nuclear Non-Proliferation Treaty, sought to limit the number of states with nuclear weapons by dividing the world into nuclear weapon states and non-nuclear weapon states. And under this arrangement, the recognized nuclear powers pledged to work toward disarmament, while other countries agreed not to pursue nuclear arms in exchange for access to peaceful nuclear technology. And this treaty introduced both political commitments and technical verification measures through the International Atomic Energy Agency, which developed inspection regimes and safeguards to monitor nuclear materials. And in the 1970s, the Strategic Arms Limitation Talks produced agreements that placed caps on certain categories of weapons and delivery systems, reflecting the recognition that technological advances such as MIRVs could destabilize deterrence. And subsequent treaties like the Intermediate Range Nuclear Forces Treaty of 1987 actually eliminated entire classes of weapons, showing that international negotiation could impose technical limitations on the engineering and deployment of nuclear systems. And beyond these formal treaties, there were also informal constraints imposed by technical realities, such as the difficulty of producing fissile materials, which required massive industrial infrastructure and advanced technology. And this served as a natural barrier to proliferation, because only a handful of nations could realistically build and maintain such programs, and efforts to monitor the spread of centrifuge technology, reactor designs, and reprocessing methods became a key part of non-proliferation strategies. And technical limitations also shaped safety measures, with treaties encouraging the use of permissive action links and other secure arming systems to reduce the risk of unauthorized use. And as computer simulations and high-performance modeling advanced, treaties like the Comprehensive Nuclear Test Ban Treaty of 1996 gained traction, relying on the idea that nations could maintain their arsenals through laboratory work and subcritical tests rather than full-scale detonations. And although not all states have ratified this treaty, its existence shows the continuing role of agreements in shaping the technical path of nuclear weapons, and the interplay of treaties and limitations demonstrates how political will and engineering realities are intertwined. Because while nations may aspire to certain capabilities, both legal restrictions and technical obstacles define what is possible, and the history of nuclear treaties reveals both successes and failures. Successes in reducing global testing and curbing proliferation, failures in achieving complete disarmament or universal compliance. Yet each step reflects the recognition that nuclear weapons cannot be treated as ordinary arms, but require special management, verification, and limits. And thus the framework of international treaties, combined with the inherent technical challenges of nuclear technology, has played a decisive role in shaping the development, deployment, and potential use of atomic and thermonuclear weapons, highlighting the ongoing tension between human ingenuity and human responsibility. The long-term engineering lessons and historical legacy of the atomic bomb encompass not only the technical achievements that made such weapons possible, but also the profound consequences that their existence has had for science, warfare, and society. And one of the clearest lessons is that advances in theoretical physics can very quickly translate into technologies of immense destructive power, once combined with large-scale engineering, as seen in the transition from the discovery of nuclear fission in 1938 to the detonation of working bombs just 7 years later. And this demonstrates the importance of understanding the potential applications of scientific breakthroughs before they are pursued to their limits. And from an engineering standpoint, the atomic bomb highlighted the need for precision, because designs like the implosion system of Fat Man required synchronization of dozens of detonators within millionths of a second, proving that even small errors could cause catastrophic failure. And this emphasis on precision influenced later fields such as aerospace, computing, and materials science, where tolerances became tighter and standards more exacting. And another lesson lies in the scale of the Manhattan Project, which showed that engineering challenges of unprecedented size could be overcome by mobilizing vast resources, industrial capacity, and interdisciplinary collaboration, setting a model for future large-scale projects in energy, space exploration, and high technology. And yet the legacy is not purely technical, because the atomic bomb permanently altered the relationship between science and society, demonstrating that engineers and scientists bear responsibility for the uses of their work. And many participants later expressed regret or ambivalence about their role, fueling debates about ethics, secrecy, and the responsibilities of researchers. And on a broader scale, the legacy of nuclear weapons reshaped global politics, creating a world where deterrence and the threat of mutual destruction became central to international relations, and this in turn influenced how nations invested in engineering, focusing on missile defense, early warning systems, and hardened infrastructure, all of which stemmed from the existence of atomic and thermonuclear arsenals. And in terms of civilian applications, the technologies developed for nuclear weapons also laid the groundwork for nuclear power, isotope production, and radiation medicine, showing how engineering born of destructive aims could later be adapted for peaceful purposes, though always shadowed by the dangers of proliferation. and the environmental and health consequences of nuclear testing added another layer to the legacy. As fallout spread across oceans and continents, and generations of people were exposed to radiation, reminding engineers and policymakers that technical success can carry hidden costs that emerge only over time. And as decades passed, the challenge of maintaining nuclear arsenals without testing led to advances in simulation, computational modeling, and subcritical experiments, creating a new generation of engineering techniques for predicting and controlling complex systems. And thus, the atomic bomb indirectly spurred progress in fields ranging from high-performance computing to seismic monitoring. And the historical legacy also includes the cultural and psychological impact, because the image of the mushroom cloud became a universal symbol of destruction and a reminder of the power of human engineering, both to create and to annihilate. And in studying this legacy, one sees how the bomb serves as both a warning and a lesson. A warning of what can happen when technical capacity outpaces ethical reflection, and a lesson that engineering is never isolated from its consequences. And so the long-term engineering lessons and historical legacy of the atomic bomb continue to shape our world today, reminding us that the pursuit of knowledge carries with it the weight of responsibility, and that the history of this weapon is inseparable from the broader history of human ingenuity, ambition, and survival.